Welcome to the differential equation class. Today we will discuss in chapter 1, Introduction to Differential Equation, section 1.1. Let's start from the definition and terminology. So the objective of this video is to define the differential equation, classify the differential equation by type and by its linearity. Differential equation, let's define the differential equation. An equation containing the derivative of one or more unknown functions or dependent variable with respect to one or more independent variable is said to be differential equation. So let's take an example. So the derivatives dy over dx, or we can also represent y prime or f prime of x, where y is a function of x. If an equation containing the derivative of y or the derivative of one or more unknown functions with respect to one or more independent variable is called differential equation. So here let's find out which one is unknown function and which one is dependent and independent variable. So here in the derivative dy over dx, the top variable is unknown function. Unknown function, or it is also called dependent variable. And the bottom part, the bottom variable x is independent variable. Independent variable. So independent variable, dependent variable, and dy over dx is the derivative of y with respect to x. So any equation containing this is called a differential equation. So we will see more example in the next step. So before that, let's classify differential equation first. Ordinary differential equation. So we have an ordinary differential equation. So if a differential equation contains only ordinary derivatives of one or more unknown functions with respect to a single independent variable, remember, with respect to a single independent variable, it is called ordinary differential equation. So when you look at back here, differential equation, here it says the differential equation containing the derivatives of one or more unknown functions with respect to one or more independent variables, right? But the differential equation which contains a derivative of one or more unknown functions with respect to one independent variable is called ordinary differential equation, and two or more differential equation is called partial differential equation. So let's focus first on ordinary differential equation. So for example, let's say that dx over dt plus dy over dt equals 2. Okay, so here you can see x is dependent variable and y is dependent variable which depends on t. So in this equation we have two unknown functions which only depends on a single independent variable which is t. So this is ordinary differential equation. Or we can take another example. Let's say that dy over dx equals x. So here again we can see y is dependent variable and x is independent variable in this case. So it is ordinary differential equation. So let's look at the partial differential equation. An equation involving partial derivatives of one or more unknown functions of two or more independent variables is called partial differential equation. So let's take an example. Del u over del x plus del u over del y equals, let's say that any function of x and y. So here you can see, as I said earlier, the top is unknown function, which is u. U is unknown function, or you can say the dependent variable, which depends on x and y. So u depends on x and y. And this differential equation contains the derivative of unknown variable with respect to two independent variables, which is x and y. So it is called partial differential equation, and we denote by this letter, delta, cursive d. Okay, so let's take another example. Du over dx equals negative dv over dy. So in this equation, we have u as a unknown function which depends on x and y, and v is another unknown function which depends on x and y. So this is a partial differential equation. Let's look more example. So this example. So we can see dy over dx plus 5y equals e to the x. So this is ordinary differential equation, and you can see this is the first derivative. This is first derivative, and you can see y is on the top of that derivative. So y is dependent variable, and x is in the bottom of this derivative. So x is independent variable. And in this example number 2, you can see y is in the top, so y is dependent variable, and this is second order derivative. So this is second order, and y is unknown function, and x is independent variable. When you look at number 3, in this example, you can see x is dependent variable, or you can say unknown function, and y is also unknown function, and they both depends on t. So t is independent variable. Here x and y are unknown function. So this equation has the derivative of two unknown functions with respect to a single independent variable, which is t. So that's why it is ordinary differential equation. And let's look at this example, del square u over del x square plus del square u over del y square. So you can see here u is in the top of on the top of derivative. So u is unknown function, right? But u depends on x and y because x and y are on the bottom of that derivative. So these are independent variables. Here you can see u is a function of x and y, u depends on x and y. So that's why this differential equation has one unknown variable, but it contains the derivative of one unknown variable with two independent variables, so it is partial differential equation. And similarly, we can see here u depends on x and t. And here we can see that u depends on x, y, and v depends on x and y. So this is partial differential equation. So let's just remind you, partial differential equation has two or more independent variables. While this ordinary differential equation, ODE, has one independent variable. So this is the main difference between ordinary differential equation and partial differential equation. Next, notation. So throughout this text, ordinary derivatives will be written by using the Leibniz notation. So dy over dx is the Leibniz notation. This is the first order. This is called first order. And this one is d square y over dx square is second order derivative. And this is dq y over dx cube is third order derivative, and d nth y over dx nth is nth order derivative. And we can also represent this derivative in a prime notation. So dy over dx can be represented as y prime, d square y over dx square can be written as y double prime, and so on. So let's look at this example. Dy over dx plus 5y equals e to the x. So we can also represent this differential equation in terms of prime. So it will be y prime plus 5y equals e to the x. And the next example, we can write this example in terms of prime, y double prime minus y prime plus 6y equals 0. And the next example here, x prime plus y prime equals 2x plus y. Okay, and in this example here, we can write x double prime plus 16x equals 0. Okay, so in this case, you can see x is on the top of that differentiation or derivative. So x is unknown function, or you can say dependent variable. And t is independent variable. However, when you look at this equation, x was in the bottom of that derivative. That's why x was independent variable, but in this differential equation, x is dependent variable. So you have to look at what is in the numerator and the denominator of the derivative, and you have to figure out which one is the dependent variable and independent variable. Next, note, you should always be aware that in a physical science and engineering, the Newton's dot notation. So we sometimes use dot notation to represent the derivative with respect to time. For example, let's say that s dot. So s dot means that derivative of s with respect to time t, which represents the velocity, where s is a position of any objects. So s double dot means that d square s over dt square, which represents acceleration. So if I give you an example, d square s over dt square equals negative 32, it can be written as s double dot equals negative 32. This one and this one is same. So we only use dot notation with respect if the derivative is with respect to time. Otherwise we use prime notation. And partial derivatives are often denoted by subscript notation. So when you look at this differential equation, so this is a partial differential equation since u depends on x, since you can see u is in the top of that derivative and x and y are on the bottom of that derivative. So u depends on x and y. And this is a partial differential equation since we have two independent variables on this differential equation. So we can represent this differential equation as follows. uxx. This means that differentiating u with respect to x twice, or you can say second derivative of u with respect to x, plus uyy equals 0. And similarly, we can represent this differential equation in terms of subscript. uxx equals u's of t minus 2 u's of t. And this differential equation can be represented as u's of y equals negative v's of x. So we always use subscript notation to indicate the independent variable in the partial differential equation. Now we will classify the differential equation by order. The order of differential equation, either ODE or PD, is the order of highest order in the equation. So you have to look at the highest order of the derivative. So when you look at this example, d square y over dx square plus 5 times dy over dx whole cube minus 4y equals ex. So what would be the order of this differential equation? So when you look at the derivative of this one here, so this 2, that means it's a second order. Second order. Second order. And when you look at the next derivative, it is first order. dy over dx is the first order. However, we have here cube, that is degree, not the order. So now these two derivatives, among these two derivatives, which one is the highest? The highest is second, right? 2. So that's why it is called, so this differential equation is called a second order ordinary differential equation. Next, note that a first order ordinary differential equation sometimes can be written in the differential form. Okay, so ordinary differential equation can be written in differential form. So how does it look like? So it looks like m of xy times dx plus n of xy times dy equals 0. So this is the differential form. So here we have an example. y minus x times dx plus 4x times dy equals 0. So this is a differential form of first order. So we can write it in a differential equation form or in a differential equation form by dividing. So let's divide both sides by dx. So when I divide both sides by dx, that means here I'm dividing by dx. Okay, and I will get y minus x times dx will be cancelled out, and it will be 4x times dy over dx equals 0. So here we can see the highest order of the derivative is 1. So this is a first order ordinary differential equation, or we can also write this in terms of this way: 4x dy over dx plus y equals x form. This is equivalent of differential equation form. And let's look at the next example. So here it is given that the differential equation form, let us write in a differential form. Okay, so to write it in a differential form, we will multiply by dx. So multiply by dx. Then when you multiply by dx on both sides, if you multiply dx and the whole things by dx, then this dx and dx will be cancelled out, and it will be 6xy dy plus x squared plus y squared times dx equals 0, which is in the differential form. So any equation of the form m of xy, so you can see m of xy dx plus n of xy dy equals 0 is called differential form. So you can write dx first and then the dy later. Okay. All right. Now let's look at nth order ordinary differential equation. So this is the general form of the nth order ordinary differential equation. F of x, y, y prime up to y nth equals 0, where f is real valued function of n plus 1 variable. So this is the general form of the nth order ordinary differential equation. So we can write that nth order differential equation into this form: nth derivative of y on the left side and everything on the right side, where f is a real valued continuous function, and this type of equation is called normal form of this general form of nth order differential equation. So we can see here, for example, dy over dx equals f of xy is first order differential equation in normal form, and this one is second order ordinary differential equation in normal form. So by solving for the derivative dy over dx, the normal form of the first order differential equation. So let's look at this example here. So this is the first order differential equation, and we will try to solve for dy over dx. Which is, we can solve, so we can find dy over dx by subtracting y on both sides. This will be cancelled out, and x minus y, it will be on x minus y on the right side, and then we will divide both sides by 4x and 4x, and we will get this relation. So dy over dx equals x minus y over 4x, which is the normal form of that general ordinary differential equation, first order ordinary differential equation. So similarly, by solving for the derivative y prime, the y double prime, the normal form of second order ordinary differential equation, this is y double prime equals y prime minus 6y. That means the highest order derivative is on the left side and everything is on the right side. Now we will classify the differential equation by linearity. So basically in this class we will learn ordinary differential equation. An nth order ordinary differential equation is said to be linear if f is linear in y prime and up to y nth. This means that nth order ordinary differential equation is linear when star, that means let's go back, where is star, this is of this form. So when you look at this equation here, you can see a n x y to the n plus a n minus x y to the n minus 1 plus up to a1 x y prime plus a naught x y minus gx equals 0, or we can also write into this form. That means gx can be written in the right side. So when you look at back here, this this differential equation, y nth means that nth order, and y n minus 1 means that n minus 1th order, and so on, right? And you can see the coefficient of y nth order derivative is a n x. That means this is the coefficient of nth order derivative, right? So these are the coefficients of each derivatives. Okay, so that will help us to see whether the differential equation is linear or not. So if the coefficient of, let me write it down, if the coefficients of y, that means this, y prime, that means this, the coefficient of this is this, y double prime, and so on, y prime, are either constants or function of x. Functions of x. So if these coefficients are either constants or function of x, and this g of x is function of x only, then we say that this differential equation is a linear ordinary differential equation. Otherwise it will be non-linear differential equation. So you basically have to be careful with this one. The linear differential equation is that there is no product of a function yx and its derivatives, and neither the function or its derivative occur to any power other than the first power. I'm saying that power instead of order, okay? Power. So we also should be careful that it should not be the functions, neither the function or its derivative are inside of another function. For example, square root of y prime or e to the y or sine of y. Okay? Otherwise it will be non-linear. And when we solve a linear differential equation, we can solve linear differential equation, and the solutions are unique. However, the non-linear differential equation cannot guaranteed to be solved. All right. So if the differential equation cannot be written in this form, then it is called nonlinear differential equation. So let's look at some example, which one is linear and which one is nonlinear. So when you look at this example number A1, so you can see this is in a normal, this is in a differential form, right? So let's change it into the differential equation form first. So I'm going to divide both sides by dx. So when I divide both sides by dx, this term will be y minus x plus 4x dy over dx equals 0. And you can see this is the first order because this is the, because of this is the first order linear differential equation. Why? Because here you can see the coefficient of dy over dx is 4x, which only depends on x, and this is a gx term, and this is y, and its coefficient is just 1. So this is first order linear, remember, linear ordinary differential equation. And let's look at next example. This y double prime minus 2y prime plus y equals 0. So in this case, the coefficient of y double prime is 1. The coefficient of y prime is negative 2. And the coefficient of y is just 1. So they all are constant. So this is again the linear, right? But the second order, because the highest order is 2. So second order linear ordinary differential equation. So let's look at the next example, this example. So the coefficient of dq, or third order derivative, is x cubed, which depends on x, and the derivative dy over dx, the coefficient of dy over dx is x, so it depends on x, that's okay. And the coefficient of y is negative 5, which is constant, that's okay. And this term is just a function of x. So that means this is a linear differential equation, and it is a third order. Third order because the highest order is 3. So third order linear ordinary differential equation. Now let's look at the next example, number B. So when you look at this differential equation, you can see y prime is here and its coefficient is 1 minus y, which is not a function of x or constant. It is a function of y. It is multiplied by y. Because of that, this is nonlinear differential equation. So the nonlinear term is here. Nonlinear term is this term, coefficients depends on y. So that's why it becomes a nonlinear term, because the coefficient depends on y. So that's why it is enough so to say this differential equation is nonlinear. So this is first order because the highest order of this differential equation is 1. First order non-linear ordinary differential equation. Let's look at the next example, this differential equation. So this is the second order, but and its coefficient is just 1, which is okay, which is constant. But when you look at this term, this is sine y, which is non-linear term. So because of this sine y, it makes non-linear term. So non-linear function of y. So that's why it is second order non-linear ODE. And let's look at the next example here. So the coefficient of fourth derivative is 1, which is constant, that's okay. But when you look at this, y square, So the nonlinear term is y square because the power of y is not 1, which is 2, right? So if the power of y or derivative of function is other than 1, then it will be a nonlinear. So nonlinear term is this one, because the reason is the power is not 1. So that's why it is fourth order. The highest order is fourth. So fourth order nonlinear ordinary differential equation. Alright, so that's all in this video.